Okay. Very good morning, everyone. Nice to see you, so many people on a Saturday morning. So my talk today is about some math around IPL tournament, specifically about the points table. Okay. So how many people watch IPL matches? Okay. So even if you have not watched, I'm sure many of you would have followed the points in newspapers, right? So you don't need to know much about cricket to even follow what I'm going to talk about, so don't worry about it. So how many teams were there last year? 8 teams. And how many matches did everyone play in the league tournament? 14 matches, right? So everybody played with everybody else exactly twice, right? Okay, good. So this was the typical points table you would have seen, right? So this tells you played, number of matches played, won, lost. No, net run rate, it is this. No result, points, net run rate, okay? So for our purpose, I'm just going to be focusing only on the first 2 columns. Don't worry about anything else. We just care about how many matches everybody played and how many they won, okay? So these are the 2 columns which are going to be important in our discussion, right? So here is another typical, so here is a points table where let's see, some team has played only 3 matches, but some has played 5 matches, okay? So here is another where people have played, 8 and 9 matches. So it's somewhere in the middle of the tournament. This is that table I like because everybody has synchronized. They have played 13 matches each, right? This is just before the final. Everybody has to play 1 more match. And this is after that, and this is the final table, okay? So now, somehow what I like these tables where everybody has played exactly same number of matches, okay? So maybe some team complains, maybe CSK would complain that, look, KKR has played 2 more matches than me, so they have some advantage. There's some problem with fixture, or maybe KKR would complain that, look, there are teams who have played only 3 matches and you've made me play 5, I'm tired, so there is some disadvantage. So there are some complaints. So what we want to do is, so here is my question. Can you design your fixture? So now you are the tournament director, okay? You're going to design the fixture with the following property, that at some point, everybody has played exactly, I want everybody to synchronize. Everybody has played exactly 1 match. And then they play. And then someday, at the end of some day, everybody has played 2 matches. And then they play some matches at the end of it. So nobody moves to the 3rd round until everybody has played 2nd match. Everybody has finished 2 matches, right? So my question is, you have all, paper and pen. So let me make life simple for you. There are no 8 teams. Let's work with 4 teams. Let's call them A, B, C, D. And every team plays against every other team twice, as in the standard IPL tournament. There are only 4 teams. Now my question is, can you design a program? So what do you mean by design? You tell me who plays the first match, who plays the 2nd match, who plays the 3rd match, right? Such that they all synchronize, right? At the end of some day, everybody has played 1 match. And at the end of some day, everybody has played 2 matches. At the end of some day, everybody has played 3 matches. And totally there are 6 matches because 4 teams, everybody is playing everybody else twice. So totally 6 matches. And is this possible? I'll give you 2 minutes, 5 minutes, just work it out and see if you can. There are 4 teams, A, B, C, and D. You can tell me, okay, A and B play first, then B and C play something, I don't know. So you tell me how they should play so that nobody moves to the next round until everybody has finished that number of matches. Is it possible? Yes, I heard some yeses. Yes? Okay. So what would be such a fixture? Yeah. Okay. 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 Right. So what he is saying is something like this. So A and B play, and then C and D play next match. So at the end of this 2 days, everybody has played exactly one match, right? Then maybe A and D play, and then C and B play. At the end of this, everybody has played 2 matches. Nobody has moved to the third round yet. Okay? And then you finished with 3, and you can sort of repeat this for the next round as well, so that you have a synchrony of everybody has played the exact number of matches at the end of some day. Okay? What if there are 5 teams? Can you do the same? No. Okay. What is not possible? So, for example, you can't synchronize to have everybody played exactly one match, right? But can you synchronize to have everybody played exactly 2 matches? Yes? How is that? So, A, B, C, D, E, okay. So, at the end of, everybody has played 2 matches. What are the matches they have played? A, B, C, D, okay. B, C, D, right. If you look at it, so this synchrony is possible at, there are 5 players. At the end of some day, I want everybody to have exactly 2 matches, right? This is what are we doing? In your points column, I want the first column to have the same number someday, right? With 1, it's not possible. I don't know, really. I mean, you all said not possible. I don't know it's possible. But that doesn't mean that somebody else will come and tell me that it's possible. But I don't know. We'll come to that later. But for 2, it's possible. What about for 3? No, I see. Why not? Well, why not is a question we will address it later. But somehow you tried, and you can't synchronize to get everybody has played 3 matches, right? And what about 4? It's possible, right? Because, simply everybody plays everybody else once. At the end of it, you have 4 matches, right? Yeah. So, A plays with B, C, D, E. B plays with A, C, D, E, and so on. So, everybody plays with everybody else. At the end of it, you have 4 matches everybody has played, and you can repeat this to get, 3 matches, right? Okay, so what have we learned? If there are 4 teams, you can synchronize to have everybody played 1 match, 2 matches, 3, 4, 5, 6, and all that. But with 5, we have a little bit of a problem. If I want to get everybody synchronized to 2 or 4, which is possible, but 1 and 3 seems like that's not possible. I mean, at least we've tried, we don't know, right? Now, that's not. Can you really confirm that that's not possible? Because you all tried, I couldn't get it. Does that mean that it's not possible? Right? What do we need in math to say that something is not possible? You need a proof. Very good. Okay. So you need some sort of an argument, right? Now, the other thing is, what about 6 teams, 7 teams, right? This is how math works. We've did some experiments with some small numbers. We found that something is possible, something is not possible, and we want to think in general. What about for general n? There are n teams, and I want to synchronize so that everybody has played 17 matches one day. Is that possible? We want to answer these kind of questions. So why is it that sometimes it's possible, sometimes it's not possible? What is the math behind this? How do we model this problem? Okay, these are the kind of questions we're going to be looking at the next half an hour or so. Okay, so how do we model this problem? And that takes me to this notion of graphs, which mathematicians, discrete math, computer scientists spend, we engage with graphs quite a bit. You would have seen some graphs, but you would have seen a graph like this. This is not the graph I'm talking about. Okay? I'm going to introduce you a notion of graph using which we will model this problem we are looking at and we'll talk about it. But the graphs you have seen in your class, in your 8th standard, 9th standard, is this kind of graph where we plot x, y coordinate. This is not the graph I'm talking about. There may be other kind of graphs. If you have learned some statistics, you'll talk about some bar graph, right? Something like this. No, this is also not the kind of graph I'm going to be talking about, but the kind of graph I'm going to be talking about looks like something like this. Okay? It has, how many people have seen this notion of graphs? Good, not many, well, hardly any. Okay, so what is, I'll define what a graph is, but basically it has a certain set of points and some lines joining some pairs of them. That is a graph. Okay? It has a certain set of points and some lines joining some pairs of them. So this is a graph. What I've drawn is a graph. This is a graph, right? This is a graph. It just has a bunch of points and some pairs of points are joined by, line is only for pictorial representation. Think of a graph as a collection of two sets. One set is a set of points and the other set is a subset of pairs of these points. Okay, they are called edges. Okay, so what is a graph? It consists of points and lines. More formally, a finite set of elements which we call vertices, and some pairs of them are called edges. Okay, so I'm going to be using this word vertices and edges. So edges are some pairs of points. Edges can be directed. There can be an orientation from here. Okay, so this could mean that in the game between A and B, A won against B. To interpret that, you may actually want a directed edge. Right? Undirected edge means that there is a symmetric relation between this pair of points. Directed means that it's not a symmetric relation. There is an ordering implicit here. Sometimes you can have a multigraph. You may have two edges between them, a pair of points. Then it's called a multigraph. Okay? Graphs are everywhere. They model, points can be Facebook accounts, and then lines can be, the links connecting them. If you both are friends, you will draw an edge. That's a graph, right? It could be a directed graph. You can say that I am his friend, but he's not my friend. Okay, so it could be directed in one direction. It could be undirected, directed. Graphs model electrical networks, road networks, right? You can have intersection points as points and road connecting pairs of points as an edge. So, for example, if your Ola car wants to figure out the shortest route from here to here, or Ola share wants to figure out who's going in this direction, the model which is sitting inside, which models the road network, is a graph. Set of points and lines, and you study about properties of these graphs. You want to look at efficient algorithms on these graphs, and this is a major study of problems, research in computer science, in discrete maths, and so on. Okay. So graphs pretty much model any kind of relation. Whenever you have a set of points and a few of them. So when I say edge is a pair, I'm modeling binary relations, but there are generalizations where you can model relations which have take more than pairs of elements. Okay. And the only other concept I need, I don't want to throw any more terminology. Degree of a vertex means the number of, so a vertex, number of edges it is part of, right? So degree of this vertex, A is in this graph is 3 because there are 3 edges in it. If you look at B, the degree of B in this graph is 2, right? Now in a directed graph, I may also talk about out degree and in degree because there are edges going out because the edges have directions. So you can talk about edges going out, is number of edges going out is the out degree. number of edges going in is the out degree, in degree, right? So good. Now let's go back to our question which we asked, that can you design a fixture so that in a team of 5 players, everybody has played exactly one match? How do you translate that into the graph theoretic question? I've written there, right? Is there a graph on 5 vertices? Because how do you model your teams and plays as graph? Because every team is a vertex, and whenever a pair of teams play, you draw an edge between them, right? A and B play, you draw an edge. Now the question I'm asking is there a graph on 5 vertices such that the degree of every vertex is exactly 1? Or the degree of every vertex is exactly 3? Right? This is the kind of question I'm asking. Well, you all said no, and we're going to now try and come up with some sort of a proof, right? Because you said you need a proof to argue this. Okay. So here is the first observation on graph on the degrees. So suppose I sum all the degrees of a graph, right? So let's look at this graph. So what is the degree of this vertex? 3, right? It's a multi-graph. Degree of this vertex, and this is 2. If I sum them, it's 8, okay? Well, if I say the graph is actually this, I could say that. Then the degree of this vertex is 1, this degree is 1, and the sum is 10, okay? The degree of every vertex here is 3, so the total degree is 12. The total degree is 10 here. Now, do you see some pattern, something about, can you? Okay, even number, okay, it looks like. Good start. More precisely, I want to say something more about. Sorry? Always comes in pair. Sum of the degrees is one number. Double, who said this? Double of the number of edges. Let's check that here. How many edges are here? 1, 2, 3, 4, 5 edges. Wow, looks like it's correct here. How many edges here? Right, 1, 2, 3, 4, 6 edges, right? 5 edges here. Okay, so, seems to be true on 3 examples. And you all told me that that's not enough to tell me that that's correct. What do you need? A proof. Can somebody give me a proof that if you sum the degree of vertices of any graph, that sum is actually twice the number of edges in the graph? Some argument, okay, something. Somehow, okay, it's actually a one-line argument, so it's not hard. So what are we counting in the degree, right? When I come here and look at the degree here, I'm counting this edge, this edge, this edge, right? Yeah. Why? How? Yeah. Yes, that's correct. So where is it counted? Right. Right. That's it, right? So if you look at any edge, it's counted in, so if the edge has 2 endpoints A and B, it is counted in A's degree as well as in B's degree. So every edge is counted twice. So that's a proof that the total number of edges, the sum of the degrees is, oh, was this open all already? Okay, it's supposed to be like this. Okay. So 2 times the number of edges. You looked at it before answering? No, good, okay. So what does that mean? That means if you sum, so if I model my points table as teams are the vertices, and whenever two teams play, I draw an edge. Then the first column, which tells you the number of the games played by each team, when I add the first column, what do I get? Even number. What is that number exactly? Twice the number of matches you played. So when you add the numbers in the first column, that is exactly 2 times the number of matches you have played. Why? Because the same argument, right? Because any match is played between 2 teams, so that is counted for the number of games played by this team as well as by this team. So every match is counted twice. So when you add this number in the points table, you can do a quick check. The first column sum is always 2 times the number of matches. So it is an even number. Okay? So now, can you have a graph on 5 vertices where every vertex has degree 3? Well, what will be the total degree? 15. That's not an even number. So you cannot have a graph on 5 vertices with every vertex having degree 3 or a degree 1 or any odd number, right? So that's a proof, right? Simple enough. So this is sort of the first. More importantly, it's that. So let's go to this graph and let's look at those vertices having odd degree, right? How many vertices are here with odd degree? All the graphs. Okay, all of them have odd degree. What about here? Here also all of them have odd degree. Okay. Here? Yeah. Here it's 0, right? Everybody has even degree. So let me just have some mixed. Okay, so how many vertices are here with odd degree? So this is a vertex with degree 3, this is a vertex with degree 3, right? So now, here is another corollary of whatever we have seen. We said that sum of the degrees of all vertices in any graph is twice the number of edges, and it's an even number. Now here is another little more specific statement, that if you go to your graph and count the number of vertices with odd degree, that number must also be even. Why? Because my total degree is sum of vertices where degree is even plus sum of vertices whose degree is odd, right? You all understand this notation, sigma, right? Sigma means that I'm going to sum over all vertices. So I'm just counting only the even degrees. Here I'm counting the odd degrees. Okay? And I know that this sum is the total degree, which I know is even. Right? But this sum is always even, right? You add any number of even numbers, you get only even number. Okay? But what about odd numbers? So if you have odd numbers, if you add odd number of them, you will get odd number. If you add even number of them, you get even number. Okay? So for maybe I should stay. Yeah. So since that is even, this number must be even. So sum of odd degree vertices is even. So there must be even number of odd degree vertices. Okay? So this is. Now this is this also has a handshaking lemma. Okay, if you go and Google out handshaking lemma, you will see this. Okay, what it says is you have a party where some pairs of people do some handshaking. At the end, you ask everybody how many people did you shook hand with, and count the number of people who shook hands with odd number of them. You will see that it is always an even number. And the answer is this, because when you do a handshake, it is counted for both people. Okay? So this has, there are several versions of this problem. It's a simple problem. It just looks at odd, even, and you have this thing. So in the points table, the sum of the first is always even, so there cannot be a graph on 5 vertices. So that's a proof. Okay? Good. That's question number 1. So now I'm going to question number 2. Here's another, we wanted the first column to have all numbers the same. That's what we worked out. Now I have a different question. Can you design a fixture so that at the end of some day, everybody has played different number of games? I'm not asking every time, someday, right? And let's make life simple. I made some example. So that let's say there are four teams again. There are 4 teams. Everybody plays against everybody else twice. What I'm asking for is that in my played table, all numbers must be different. Someday, not every day, someday, can you design a fixture so that at the end of some day, everybody has played different number of games? Okay? I'll give you 2 minutes to work it out. So is the question clear? Yeah. So let's say there are teams A, B, C, D. Oh, by the way, I'm not asking for you to get exactly this table. Okay? I don't know whether this is possible. All I am saying is all the 4 numbers must be different. Some 4 numbers. Everybody plays everybody else twice, okay? Because everybody plays everybody else twice. Can you tell me the graph? What are the edges? What are the games played? You can't have 7 and all, right? How many edges? Maximum, how many matches anybody plays? Into 2. 6. So you can't have 7, 8 and all. Maximum 6 is what you'll have. Yes, go ahead. A plays 4, B 3. Okay. Okay, what are the matches? A, okay, fine, go ahead. A plays 2 games with B, 1 with C. A also plays with D. Okay. Excellent. So that is the graph. Thank you. Nice. So I have 1, 2, 3, 4 is degree here, 3 here, 1 here, 2 here. I could also have another one where A and D don't play. Then what would be the numbers? 0. No, sorry. No, I think it's needed. Okay, there are other options. Okay, let me just see if what I had in mind was. Yes, what about this graph? I have 0 here, 1 here, 2 here, 3 here. Okay. All numbers are different. Everybody plays at most 2 matches and 4 teams. Okay? Can you try with 5? Yeah. A plays 2 with B. Okay, let me call this E. B plays 1 with C. Okay. Okay. Great. So this degree is 0, this degree is 1, 2, 3, 4. Okay. Thank you. Good. Okay, you can ask all kinds of questions here. Now let me suppose I tell you that every team plays against, so these are multi-graphs, right? Because I have 2 edges. Suppose I tell you every team plays against every other team only once, okay, or at most once. Now can you have all degrees different? No, why not? Because it looks like I had some S answer for a couple of questions, so something must be no, right? So what I want is that every team to have played different number of matches, but you're allowed at most 1 with any other team. No. Okay. I've got some no's. Just because you tried and said no, I am not going to believe it, but maybe somebody else will. Unless you're going to give me some proof. Okay, somebody wants to give a proof that it's not possible? Yeah, okay. You want it. Okay. I'm not asking about 1, right? You're allowed. No, 1 against everybody, but you are allowed to play with any of your partners, right? Any of your teammates. So I'm not asking 1, 1, 1. I'm just saying you're allowed at most once, but you can't have a multi-graph is all I'm saying, right? Somebody else had an argument? Yeah. Sorry? So you're saying it is possible is what you're saying. Okay, okay. Pentagon with, but there are only 4 teams you're talking about, but 5 teams, okay. Mm-hmm. Everybody has 2 matches now. So that will be like 4 or whatever, 3. Every single combination happens once means everybody would have played 4 matches. But I want all the numbers to be different. Not possible. Any argument? Okay, so sorry? I know, that's what you want to prove, right? Not possible means what? Not all numbers can be different. At least 2 of them should have the same number. That's what we want to prove. Why? What's an argument for it? Okay, here is a proof, right? I'll start. Maybe you will complete. Okay. So I have all 5 teams to have different numbers. What are the possible different numbers? 0, 1, 2, 3, 4. There are 5 teams. 5 cannot be there. Maximum 4, right? 0, 1, 2, 3, 4. These are there are 5 teams and you want to distribute these 5 numbers to them. So everybody should have 1 number, right? So somebody must have played 0, maybe B, A might have played 4, this might have played 2. If there is such a thing at all, then if I want all these numbers to be different, there are only 5 numbers, 0, 1, 2, 3, 4 possibilities, and there are 5 teams. So I have to map, everybody should have one of these numbers. Now, is this possible? Why not? A has 4. So exactly, if A has 4, how is it that B has 0? Because A has 4 means what? A has played with everybody else. So A also has played with B. So how can B have 0? Right? You cannot have 0 and 4 in my list. So really there are only 4 numbers which I have to distribute to 5 of them. So 2 of them should have the same number. Right? And some 2, we don't know. Some 2 should have same number. Right? You can generalize this for any n. Is the argument clear? If there are n players, everybody is playing at most 1 with everybody else. The possible numbers are 0, 1, 2, 3 up to n minus 1. There are only n numbers and n of these numbers I have to map each one of them. But then if somebody has 0, how is it that somebody has n minus 1? That's not possible. So that's a contradiction. So at least 2 of them should have the same number. Right? So now this is another interesting theorem. The last statement is an interesting statement on graphs. In any graph, if it is not a multi-graph, there are no multiple edges, then there must be at least a pair of vertices with the same degree. Okay? So another interesting result. We saw 2 of this now. One was that the sum of the degrees of all vertices is always an even number, 2 into number of edges. And here is another result on a simple graph. You cannot have all vertices have different degree. There must be at least a pair with the same degree. Okay. Now I get on to my last question, which is, suppose I tell you, there are 5 teams. Everybody has played with everybody else exactly once. Let's make life simple. Everybody has played with everybody else exactly once. Okay? And I tell you that some journalist reports that this is the score. Is it possible? Okay, why not? A can't be 5. Nobody can be 5. Okay. Sure. What else can you say? What on? So each number, first of all, should be at most 4, because you're allowed at most. Actually, exact at most 4. Right? This is, by the way, this is not the number of matches played. This is the number of matches won. Okay, this is the last column I'm talking about. Number of points gained, or number of matches won. Right? So now I say, if for this to be a valid score sequence, first of all, each number should be at most 4. What else? I claim the sum should be 10. Why? No. No. How many matches have been played? Why 10? 5 teams. So each one would have played 4 matches with everybody else. So it's 5 into 4 at 20, but twice the number of edges. The number of matches played is 10, and every match is won by somebody. Okay, we are assuming there is no tie. Okay, I forgot to mention this. We are going to make life simple. There are no ties at all. Everybody plays with everybody else. So exactly 10 matches played. So each match must have been won by somebody. So the total sum of this column must be number of matches, not the twice the number of matches, exactly number of matches, because each match one winner, right? Remember, this is a different column we are counting, not the number of matches. Okay, good. So if this has to be a valid sequence, one important property, that sum should be 10 and each number should be at most 4. What about this? This seems, well, just because it satisfies the condition, it doesn't mean that yes, but okay, let's try this first. Not played, it's 1, okay? Keep in mind, this column is a number of matches 1, okay? Everybody has played with everybody else, exactly once. 10 matches have been played. Now I'm telling you, these are the scores at the end. Question is this the valid score sequence? You told me each number should be at most 4. Yes, that is satisfied here. You told me that the sum should be 10. It's satisfied here. Is it a valid sequence? Why not? Okay, so let's, yeah. Okay, let's slide. I don't know whether C and D, B last to D or whatever, is it? Okay, let's try, right? So, no, but here is a very simple argument. Let's look at the match between B and E. Everybody played match with everybody else. The match between B and E, and I said there are no ties, right? So one should be 1, so at least one of them should be 1. So B, E, both 0 is not possible. Okay? So even though this sum adds up to 10 and every number is at most 4, this is still not a valid sequence because you need some more conditions on this sequence. What is the condition? Well, here is the condition that you cannot have 2 zeros. I can see, given this sequence, I want to know whether it's valid. I can start looking at more properties, more and more. Okay, this is how research is done, right? You ask an interesting question, make some interesting observations, and gradually build towards some nice characterization. Okay? So here we have an observation that I cannot have 2 zeros because when they play, somebody has to win. Okay? We are assuming there are no ties and so on. Of course, you can ask the question, what if there are ties? Yes, that's another completely different exploration. I'll leave it to you to try. Okay? But in this model, you cannot have 2 zeros, so this is not a valid sequence. Okay? What about here? There cannot be 2 4s, right? Because a 4 means what? This guy has won against everybody else. So how can somebody else also have a 4? Right? This is not possible. Okay? You can. So let's come back to this. Is this valid? Because sum is 10. I mean, you can say yes only if you give me an outcome of the matches, right? Only if you tell me the outcome, I will believe you. So what is the scenario? I have 5 teams. You have to prove either way. Okay? Let's look at the graph theoretic question I'm asking. I have a graph which is a complete graph. Everybody has played everybody else. What is your job is to give me the direction on the edges. You have to tell me who wins against whom. That gives you a direction so that the out degree of the vertex is exactly what I told you. Right? I'm giving you this number. All I'm saying is after you orient these edges, the out degree of A must be 4, out degree of B must be 0, out degree of C is 2, and so on. Is there a way to orient the edges? Because orientation gives you the outcome of the match. Yes, okay. Who's going to tell me that? Well, clearly B is 0, so let's draw B and say that everybody is coming into B, right? B has out degree 0. I'm just going to try. I'm not saying, I don't know whether there is such an outcome or not. I'm going to try based on the numbers. E has exactly 1, so E must be, let's say, this, which has defeated B, but it's going to lose against everybody else. Okay? Now I'm going to say C is 2, so this must be C. So C is 2 because it has defeated B, it has defeated E, and everything else it has lost. Okay? And now finally I have A and B, sorry, A and D. Okay? So so A is going to defeat everybody else. So that's A and that's D. So that is a realization of this score sequence, right? Now, I don't know why this is realizable, because just because every number has to be at most 4, the total has to be 10, doesn't necessarily mean that it is realizable. We saw some examples where it's not. Sometimes it is realizable. So an interesting question is, given this score sequence, when is it realizable as the out degree of such a graph, which is called a tournament, actually, right? It's a complete graph. And this question was answered in 1953 by a mathematician called Landau, and he showed that such a score sequence is valid, means that it is an out degree of such a graph, if and only if the sum of any I of them is at least IC2, and the total sum is NC2. The total sum is NC2 is what we already saw, because there are totally NC2 matches. So there must have been NC2 games 1. So total sum must be NC2. But that alone is not enough. We saw some examples where it is realizable, some examples where it's not realizable. And this theorem, 1950, so it was a deep theorem. It had some, the proof is not very hard, but it required some work to show that the only time when it's realizable is that if you sum any 2 of them, it must be at least 2C2. If you sum any 3 of them, it must be at least 3C2. If you sum 4 of them, it must be 4C2, which is 6. If that happens, and the total sum is NC2, then I can construct a tournament like this. Okay? So that takes me to the end of my lecture. So basically, we looked at 3 different questions. We saw this beautiful area of graph theory, how we can model these questions based on graphs, and some of these questions actually lead to some very interesting deep mathematics. Okay? So I'll conclude thanking you and encouraging you to ask more such questions and find your own answers. And you never know, some of them may lead you to very deep mathematics. Okay? Thank you.